Okay, this is an introduction to hyperbolas. So our definition for a hyperbola is a set of points in a plane, the difference of whose distances from two fixed points called the foci is a constant. So if you look at this, it's saying for any point on the hyperbola P, if we find the distance to one focus point, we call that d sub 1, and we find the other distance to the other focus point and call that d sub 2. That distance, d2 minus d1 or d1 minus d2, is always going to be the same. In this example, the origin is the center of the hyperbola. The center of the hyperbola is always, the center, but in this case, the origin, 0, 0, is the center. And it's always going to be the midpoint of the foci. So just like before, when we wanted the center of an ellipse, the center of the ellipse is the midpoint of the foci. It's also the midpoint of the vertices and the co-vertices. There aren't really co-vertices for a hyperbola, though. And we can still define this as PF2 minus PF1 equals 2a. So we're still defining it as 2a. If you subtract that. And the 2a comes from still the length of the major axis, going between a comma 0 and negative a comma 0. There are some differences with an ellipse, and we'll take a look at that, but this is still the same. Okay, a line through the foci intersects the hyperbola at 2 points called the vertices, so those are in red. And the ends of the pink segment would make up the co-vertices, but there aren't really co-vertices. There's vertices and then there's like endpoints of the other axis. And what happens is if you draw a box between the vertices and then surround where those not really co-vertices are. Okay, this is still at 0b and 0 negative b. But they're not co-vertices because they're not on the hyperbola. The green branches of the hyperbola are the curved parts. So the vertices are called vertices because they're on there. They're on either side of the center. The co-vertices aren't really a co-vertex because they're not on the hyperbola. But what that does is it creates a asymptote. And in this case, the slope of my asymptote is going to be b over a. And if it's a vertically opening hyperbola instead of horizontally opening hyperbola, then it would be a over b. There's still a lattice rectum length, which goes through the focus. That's an orange on the screen. The lattice rectum length is still 2b squared over a. So we're going to talk more about all these pieces. Here's my equations. Biggest difference is that we have a minus sign in front, or in the middle, sorry. Okay, that's the biggest difference. So there's a minus sign. So it's x squared minus y squared equals 1, or y squared minus x squared equals 1. Now, because the subtraction is not associative, like 1 minus 2 is not the same thing as 2 minus 1, the major axis is always defined by what comes first. So here I have a horizontal hyperbola, which means that it intersects the horizontal axis and opens left and right. For this one with the y minus k squared, if that's first, that's my major axis. Vertical hyperbola, that means it opens up and down. The center of the hyperbola is always at hk, or 0, 0 if there's no shift. This is a similar but different equation for your Pythagorean. C squared equals a squared plus b squared. One way to remember that is that c, the distance from the center to the focus, on a hyperbola is greater than the distance from the center to the vertex. So for example, on this diagram, C to F is larger than C to A. C to A is the little red line. So since C is larger, that's one way to remember. However, depending on the shape of the hyperbola, B could be quite large as well. But C squared is going to equal A squared plus B squared. From these diagrams, you don't necessarily see that the focus is larger than the B value. We also have equations of the asymptotes, again, B over A and A over B, and then kind of written in that modified point slope form. So you can jot down all these equations, you can jot down these notes, and then we're going to go through a couple problems together, and then we'll go through the rest in class tomorrow. We have the constant, okay, that eccentricity E. For a hyperbola, this is greater than 1. For an ellipse, we talked about how it is less than 1. Okay, just being very clear with eccentricity. The eccentricity is defined as the ratio of the distance between the foci on the hyperbola to the length of its major axis. Distance between the foci of the hyperbola to the length of its major axis. We didn't really look at that with an ellipse. With an ellipse, if my major axis was, okay, 2a, and then the foci, the distance between the two foci, was 2c, then that c over a that we talked about for eccentricity can be written as the ratio between the distance between the foci compared to the distance between the vertices, or the length of the major axis. So for a hyperbola, that's greater than 1, because again, from the center to the foci is larger than from the center to the vertex. We still have the directrix equation, and then if we want the definition comparing the directrix and the focus, we have that down in blue. A locus of points in a plane whose distance from a fixed point is equal to a constant times the distance to a fixed line. This blue definition is true for an ellipse, a hyperbola, and a parabola. For a parabola, E is equal to 1. For a hyperbola, E is greater than 1. For an ellipse, E is less than 1. Let's look at two problems. So my major axis is going to be horizontal because the x squared is first. So a squared equals 4 and a equals 2. So on my graph, I'm going to plot points at 2, 0 and negative 2, 0. So my major axis is going to be 4 long. The other axis, could call it the minor axis, has a b value equal to 3 because b squared is 9. So b equals 3. And I use those to help me plot my my asymptotes. Draw a box containing your vertices and these other points. And then you can use that as a slope for your asymptotes. And when you go to draw the hyperbola, you go from the vertex and you gradually get closer to the asymptote. And that's my hyperbola. If I wanted to find out where the focus is, I could say the focus is based on c squared equals a squared plus b squared. So c squared equals 4 plus 9. So c equals square root of 13. Square root of 13 is between 3 and 4, closer to 4. So root 13 comma 0. Negative root 13 comma 0. If I wanted to find the length of the lattice rectum, I could say L equals 2b squared over a still. So 2 times b squared is 2 times 9 is 18. 18 divided by 2 is 9. So I should be able to go up 4.5 boxes and be on the blue curve. From the focus, down 4.5 boxes on the blue curve. And I could graph the lattice rectum there. And then my directrix is x equals a squared over c. So that's going to be 4 over root 13, 4 root 13 over 13. Figure out what decimal that is. 4, wrong button, square root 13 divided by 13 is about 1.1. So we're going to have a directrix there and another one on the other side, and negative 1.1. So that's an example of how to use all of the parts. And we will go through another one in class. We'll start with this one tomorrow. So that's it for now.